So today we're going to talk about gradients. Gradients are pretty clutch for going through Calc 3. Also pretty clutch in computer science and data science. This is actually a thing that has a lot of relevance to your kind of daily. Gradients are actually how all machine learning, maybe not all, how most machine learning works. So first we're going to define it, then we're going to learn to calculate it, then we're going to talk about an interpretation of gradients that has to do with steepness. Then we'll talk about how gradients and level curves interact. And then finally, we'll do a little application of the gradient. So I promise, like, it sounds like a lot of stuff. It's not really so bad. The first thing we're going to need is just to know some symbology. So I'm going to tend to write something like either grad f or this funky upside down delta thing f. I'm going to call that grad f. So I'm going to read that as gradient of f. And we should talk about the category of this thing. So the category of the gradient of a function. So f's going to be a function. We're going to say, okay, this f here that I'm thinking of, that guy's going to be a function mapping like R2 to R something. So I'm going to think about that as like f as a function of x and y, right? F of x and y. We're going to have some more applications of gradients later where we might do 3 variables or 5 variables or 25 variables or whatever. It's all going to be the same stuff. It's always going to be a function of a few variables into the real numbers. And our gradient, so when we talk about the gradient of f, that's going to be a map. It's going to take R2 as a point space, right? So that's going to take x's and y's, and it's going to turn them into vectors, 2-dimensional vectors. So what we're going to get is we're going to say something like the gradient of f at a comma b is, and here's how you calculate one. I'll just show you right now. It's fx evaluated at ab, comma fy evaluated at ab. That's all there is to it. You take the two partials, shove them in a vector. When you want to evaluate the gradient of f at a point, you evaluate the two things at the point, you get a vector. I'm going to tend to write gradient of f just kind of by itself. That's going to mean the function that takes points and associates to them vectors. We'll get a little sketch for this in a second, but for right now, I just want you to know that's what we're doing. So we've got notation, we've got calculation. So to highlight, this thing here is the answer to part 1. That's how you calculate one. Okay. Let's think about gradients and steepness. So, well, I think I'm going to need to think about what does this vector maybe mean? Okay, so I'm going to think about standing at some point on a surface, right? So to draw my little picture, I'm going to think, here's the surface, right? This is my classic surface. It's got 4 corners. It's up over top of some rectangle. Oops. Bajo. Nice rectangle. So I've got a rectangle down here in the XY plane. I've got my surface that's kind of chilling above that. I'm thinking to myself, all right, if I was standing at a point on this surface and I wanted to like look in a direction, so I'm going to pick this direction here. I'm going to call that direction U. And I wanted to know how steep are things in that direction. Well, I'd kind of be asking a question about a tangent plane, right? So I'd be looking at that and I'd be saying, okay, so that vector U, which really in this case is I'm kind of thinking of a unit vector in that direction. So I'm thinking of U as a unit vector. And I'm thinking, okay, how does that work? Well, U's decomposed into some pieces, right? So I'm going to think it's a couple of pieces like this. I'm kind of projecting that U down into the plane down here, right? So this is the vector U I'm talking about. So I've got my vector U here. My vector U here looks like some kind of change in X bit, some kind of change in Y bit, right? So when I think about like, oh, how steep is it going to be in that direction? I'm just going to toss my tangent plane in there, right? And then I'm going to ask, well, if I turn and look on the tangent plane, how steep is it? Because that's really what the surface is like. So I'm literally just going to use the same stuff that I would have used to calculate this kind of tangent plane stuff, right? I'm going to say like the change in f is basically the x derivative, so that's like fx at ab, and then I'd multiply that by the change in x, and then I'd add fy at ab, and we'd multiply by the change in y there. Well, and change in x and change in y are kind of unity. Maybe I could like rewrite this, I guess. I could be like, well, it's fx at a and b, comma fy at a and b. And then I'm like dot producting with some vector that's like change in x, comma, change in y. Oh, but like I know what that is. Like I didn't really have a change in x, comma, change in y anywhere. Like I just made that crap up. I was really thinking about a direction that I was looking in, right? So this change in x, change in y crap, well, like really, that's really just my vector u, right? So I'm taking the gradient, I'm dotting with a unit vector. That's telling me how steep stuff is. Okay, cool. This was actually a bonus concept. I'm gonna call this one. Actually, screw it. I'm gonna do this. I'm gonna go like this. I'm gonna say we inadvertently just discovered directional derivatives. And really, this is going to be me saying, all right, du of f. I'm thinking about this as the rate of change of f in the direction u. Okay, cool. Bonus concept. We made up a new thing. It's directional derivatives. I want to know what's the relationship to like steepness though? So I just wrote down a concept for how do I tell if I look in a certain direction how steep stuff is. Then I might get this like motivating question. So my motivating question, oh, sorry, that was concept 2 there. Let's do concept 3 over here. Concept 3 is going to be, what's the steepest? What direction is steepest? In other words, right, another way to ask that would be to say, or when is du biggest? Well, du is just a dot product. So when is a dot product biggest? Let me do a quick, I'm gonna take this thing down here. Let's make ourselves some space. Okay, so just said du of f, right? I'm really talking about a function f, is actually just the gradient of f dotted with a unit vector. But I have some like geometry for dot products. We like made that stuff up earlier. So that's like the magnitude of the gradient of f times the magnitude of u times the like cosine of the angle between them. Okay, so these two quantities aren't changing, right? Because the gradient of f is just the size it is for a given point. The size of u is actually 1. And so the cosine's changing though. So when's cosine the biggest? Cosine's the biggest when it's 1, right? Like that's the biggest it ever gets. That's when theta is 0. So this is always smaller than the magnitude of the gradient. And it's actually equal. So the like interesting bit is equality is when theta is 0. What does theta is 0 mean? means the angle between the two things is 0. So that'd be a case where I've got like the gradient of f points this way and the unit vector points parallel to it. Oh, fucking cool. That's neat. That means I can resolve this by saying, so apparently, the gradient of a function f points at the steepest direction. And I get a bonus. The steepest it ever gets is actually the magnitude of the gradient vector. That's a cool bonus, right? So, and the steepest slope is the magnitude of the gradient. That's kind of cool. That gives me some neat tricks, actually. So let's see. Gradients and level curves. What's a level curve? What is a level curve? So when I think about a level curve, let me go get Google Maps out quick. Actually, let me go get Sartopo. Come on. Okay, so here's Sartopo. This is the mapping software we use for search and rescue. This is actually really rad. If you're into backpacking, it's also called CalTopo. Even the free version is actually really, really handy. So let's go find campus here. Let's see, what am I looking at here? There's Sonora, there's Columbia. Oh, there's campus right here. Okay, so here's campus. I'm going to turn this to, oh, those are kind of ugly looking. Let's turn it to Forest Service topos. Okay, so this is Forest Service topo maps. So I'm going to grab this thing so I can draw on it. Sorry, it's going to take a second because I'm also, oh god. Sorry, a bit of a tech hiccup running too many things here. So here I've got my topo map that I've copied into something so I can draw on it. So I'm hoping that you guys remember the level curve. So these little lines represent a place where everything's same height, right? So that means that if I stand on one of these things, so I'm going to envision standing on this one right here. Okay, so that's down in the Arboretum. You can actually go stand down there if you want. So take this video, pause it, walk down into the Arboretum, find a spot where you can stand on the hillside for me, okay? And then restart this. So standing on the hillside, and I want you to put your arms out to the sides, right? So face uphill. That's going to be your steepest direction, uphill. So turn until you're pointed uphill as steeply as possible. So in my case, that's going to be my guy's looking this way because that's the most uphill he can get, right? And then I want you to, while standing, looking straight uphill, put your arms straight out to the sides and tell me what you think your relationship to the level curve is going to be. Give you a second here. Okay, so what I'm hoping you realized is that if you're looking straight uphill, it is kind of equally bad for you to turn to either side, right? And what that means is that symmetry says that flat is directly underneath your arms, right? If you're looking as steeply uphill as possible, your arms are going to be out over your level curve. What that means is that the gradient is actually perpendicular to the level curves at all times. So we can see that if we kind of thought about like, what if I was looking here, right? So I might look here. Oops, I'm gonna have trouble drawing guys here. So I'm gonna say I'm looking here. Perpendicular to the level curve is like that. That's uphill. If I walk that direction, I'm gonna get to here. Perpendicular to that level curve is up this way. That's also as steep as I can go. perpendicular to that's up here. You guys notice what's happening there? I'm kind of climbing that hill. This process is actually called gradient ascent. So that's our application. So our answers to 4 and 5, right? 4 being what about level curves? So the answer to 4, oops, let me dump 4. So I'm going to take 4 over here. So the answer to 4 is level curves are perpendicular to the gradient. And 5, what's an application? You can get to the top of a hill by following the gradient up. You can get to the bottom by turning around, right? By following the anti-gradient downhill. Because if you're standing and you're looking as uphill as possible, behind you, straight behind you, is downhill as possible, right? Is as downhill as possible. So super easy. We get two processes out of this. We can find maximums by doing gradient ascent. We can find minimums by doing gradient descent. Gradient descent, PS, is what water does. If you put water on the ground, it does gradient descent, more or less. There's some complication, but it's pretty close. So to that end, I have created a couple of toys. So here's a toy about gradients generally. So here I've got this function, x squared y minus y squared sine of 2x, right? I just made some BS up. I'm in the kind of two-dimensional case because I don't, putting these on a three-dimensional thing kind of trips with your head. The perspective is just a little weird. You can play with it if you want, but it's a little tough to understand. These are maybe best viewed in 2D. So here I've got my point. I can drag this around, and attached to my point, I've got this little black line. That's just a parameterized version of the gradient vector, right? So this little guy here is just kind of pointing at the gradient, and I can do some exploration here, right? You can see there's some weirdness. You might notice the gradient disappears right in here. That's kind of neat. That kind of means you got to the top of something, right? See, if I'm like walking up, I'm following the gradient, I'm following the gradient, I'm following the gradient, I'm following the gradient, following the gradient, following it, following it, following it. All of a sudden it kind of disappears. You can see it's still there, just a tiny little bit, right? So let me turn on level curves here. So these wacky businesses are the level curves in my function. These are the ones from -3 to 3. And you can see that, like, anytime I'm in here, see how that gradient's perpendicular to that thing? I move it around, it's perpendicular. Isn't that kind of cool? See they're perpendicular here. So if I ask you which way is this, right? Is this uphill or downhill right here? Following the black arrow, remember, is always uphill, right? I just calculated the gradient, and so that's uphill that way. If I put it over here, we're talking about going uphill into here. That's uphill up there. That's going downhill now. See how the gradient's pointed the opposite direction I'm dragging it? So that's kind of cool. Here's another one. So I made this horrible function. It's real nasty. I'm going to let you in on a little inside baseball here. The way I calculated the partial derivatives were I asked Wolfram Alpha for them. Conveniently, you can copy and paste functions straight out of Desmos in here, and it actually pastes in with the LaTeX, which is kind of cool. And Wolfram Alpha knows how to read LaTeX. If you want to get the derivatives out in a way that you can copy and paste them, you can just hit plain text and then copy and paste this. I did have to slice it a little bit in Notepad or something, but whatever. So here I've got my function. I've got my little parameterized version of the gradient. That's the little blue arrow here. I just copy and pasted those formulas in here. And now the thing I'm after here is I want to know where the tops and bottoms of this thing are, right? So I want to be like, okay, so where's, oh, see that? I'm following this along, following it along, following it along, following it along. Feels like there might might be some kind of a hilltop going on over here. And see, I can't go any further. Every time I kind of chase it, it just kind of oscillates to the opposite side. Okay, so there might be a hilltop there. What about in here? Oh. See how to get into this one, I'm having to go against the gradient, but there's that same behavior where it kind of vanishes. Okay, so that's a minimum right there. So let's see, I can put some points on here. Actually, I'm not going to put any points on here. You guys can figure it out. So around -1, there's some maximum stuff. At 0, there's like a minimum. If I follow this thing up, whoa, okay. Feels like I might have a maximum in there, right? I climbed to the top of a hill. Let's see, what about over here? Oh, there's another hill there. What about over here? Oh, that just kind of zeroes out all over. But if I climb back up this way, zhup, 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 climbing, 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 and whoop, disappeared. Okay, so I come in this way, climbing, 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 zoop, same top. Okay, what if I come up on this way? So there's nothing going on over here. There's nothing to follow, really. Oh, there's the thing to follow. Zoop, zoop, zoop. Up, 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 up. Okay. Okay, cool. So that feels like I've isolated a couple of things, right? So we could follow in up here. Oh. Okay. Cool. So I feel like there's maybe a max in here. I found some kind of weird thing down in here. I think that's a minimum. And then there's like a maximum here. And I think there was another, yep, there's another one down here. And not in between. See that? There's a kind of a funny spot there. Oh, there might be there's something going on in between there. See that? It's a spot where the gradient does actually zero out, but it's really hard to find. And then it seems like it goes up on either side and goes down that way and down that way. So it's like up on either side, down on the other directions. It's like a saddle or something. Okay, so let me show you what this picture looks like. Here's a Math 3D version of it. See, it's got this little double-topped hill over here. It's got this weird little flat-topped thing here. And then there's that hole there. And then that thing in the middle, see how that's a double top? So there's a saddle in between there. That's kind of cool. So I was able to explore a lot of that just by kind of screwing around with this thing, right? This is actually how machine learning works. Like the way inside baseball there. So the way machine learning works is you kind of start it somewhere and then you go, okay, if I loop around this thing, what's the best improvement I can make from here? And then you go in that direction and then you loop around that one and say, okay, what's the best improvement I can make in here? And then you go that direction some more, and then you loop around and say, okay, what's the best direction I can go from here? So you just kind of wander around looking for the steepest direction, right? The kind of analogy of that on the map would be like, if I wanted to know which direction to go from someplace like, actually, let me copy this. Okay, so say I was searching for a hilltop, right? So I'm going to start like, let's see, I'm going to start right here. Okay, so I'm going to sample in a little circle around myself and say, okay, what's the highest point I got to there? I might be like, oh, okay, it's right here. That's the highest point I was able to get on that little circle. And then I'm going to sample in a little circle around that. And I'm going to say, oh, okay, what's the highest point I was able to get there? I was about here. Then I'm going to sample in a little circle around that one. Okay, what's the highest point I was able to get in there? It might be right here. Okay, we'll sample in another little circle. I was able to get to there. Sample, sample, sample. Oh, best I was able to do is here. Sample, sample, sample. Best I was able to do is about there. Sample, sample, sample. Oops, that sampling was bad. So right here, sample, 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 sample. Okay, best I'm able to do is right there. Sample, 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 sample. Everything's lower. I'm done. I got to a hilltop. Is it the hilltop I thought I would get to? No. It's just some little friggin' hilltop over here, right? I went like this. I didn't end up at top of this big hill next to it. I didn't end up on top of the biggest hill that even nearby, right? That little mound there. This is a bigger hill. I just happened to top out on some little thing. The kind of analogy to that would be you might start and end up on this lower hilltop instead of ending up on one of the two peaks. This is a thing that happens. With machine learning algorithms, we don't know what the answer is. You can't graph this function because you don't know what the function is, right? So you're just trying stuff. And what happens is sometimes you get to an answer that seems satisfactory, but you always have to wonder, is it the best possible outcome? I don't know. We could start with different training data, right? We could start in a different spot and see if we end up in a similar place. That actually is a thing that like machine learning specialists really, really worry about. For what it's worth, evolution does the exact same thing. Evolution doesn't actually do optimization in quite this way, but it does a similar thing. So what can happen is that you'll evolve to something that is kind of as good as it can get without changing really drastically. Panda thumbs are a good example. Pandas don't really have thumbs. They would be better in their environment if they actually had thumbs, but they kind of lost that part. So what they have is a bone that they can use kind of as a thumb, but it's not really a thumb. It's just something they can kind of mash to their palm, right? It'd be like if you lost the ability to make these two bones here, but retained this one. Is it good for gripping? Yeah. Is it optimal? Hell no. Like, the design of your eye is another great example. Like, your eyes put together in a way that works really fucking well. Is it optimal? Hell no. There's an opening in the back of it for your nerve. Your nerve comes in right in the center of it. And so you have a fundamental blind spot in the most important place in your vision. Like, why? Because it did it by accident, man. Like, it didn't do it on purpose. Nobody sat down with a drafting table and made an eye. It just kind of became a light sensitive patch of skin that was neat. And then that became a slightly more light sensitive patch of skin. And then at some point it became enclosed. And then at some point it filled with some fluid. And at some point it added a lens. Like, this is all kind of happenstance. It's not designed. If it was designed, it wouldn't have a blind spot in the back. Same goes for like human reproductive organs. If you weren't kind of the product of this like relatively haphazard process, there's no way in the world that your reproductive organs and your waste elimination system would be next to each other. Like, it's a terrible design. It wouldn't do that. Like, same goes for like why you get nauseous when you get motion sick. Like, it's literally just that those two pieces of your brain happen to be next to each other. And so your motion sensing area happens to abut against your like food control area. And so when the motion sensing area gets a little overstimulated, it kind of bleeds into the area next to it. It's like, why should you want to throw up when you get like rolled down a hill? Like, doesn't make any sense. It's not a good idea. You shouldn't throw up your food. There's no reason for you to do it. It's just that those two things happen to be next to each other because there's a like movement that doesn't punish it too badly in that direction, and you're now at a local maximum, right? Would it be better if they were not next to each other? Yeah, probably. But it's just the way you are. You kind of can't do anything about it now. Without making a really drastic change to the human form, we're kind of stuck with these things. We've achieved local maxima in these areas, and we're kind of stuck. It's really cool to know that this is kind of how things happen. So here you go. Gradients point in the steepest direction. That direction can be exploited to find maxima and minima. This is not how we tend to find maxima and minima mathematically, but it is a way we being the royal we of humanity, we tend to find a lot of maxima and minima this way. Is that our best option? Maybe. The optimization's hard. You remember this from Calc 1. We're going to give you a bunch of techniques for it, but gradient ascent and descent are the fundamental things that we use for functions that we don't know. So it's very cool. You see it every day. Every time you use a machine learning algorithm, every time you use a classifier, every time your phone recognizes a face in a photo, every time your Google Photos auto tags objects, every time you use ChatGPT to generate an English paper or any other large language model, like it's all gradient ascent at the bottom, which I guess makes it gradient. Whatever. All right, catch you guys later. Thanks for listening to me rant at the end here. I really appreciate it.